Okay, in this exercise, we are given that we have a mass of 50 kilograms. It's 50 kilogram stunt pilot, and we have a speed that she's flying along at is 95 meters per second, and she has a maximum radial acceleration, which she can have, or maximum centripetal acceleration, is going to be 4Gs. So AC max is equal to 4Gs. Okay, and the reason for this, when she's in this vertical circle, right? So she's kind of like dive bombing down like this, and she goes up. When she's here, so she's sitting here, and she's right there at the bottom of the circle. She has to be accelerated upwards, right? And everything in your body has to be accelerated upwards, right? It's not just your body. We tend to just treat the body as a system, but it's all the organs in the body and the fluids in the body and everything like that too, right? So what happens is, in order to keep the fluids, let's say like your blood in your brain or something like that, in order to keep blood in your brain, you have to have your blood vessels and capillaries and all this stuff be able to, in your heart, to be able to exert a force strong enough to push this this blood to accelerate it upwards, right, at this rate. If it can't be accelerated at that rate, then the blood doesn't follow a path like this, right? And so what happens is that you might actually do this. I have sometimes, if this were in person, I'd have people kind of stand up and roll your arm in a vertical circle. And when your hand gets to the very bottom, have your hand kind of stretched out. When your hand gets to the very bottom, how many fingers is that? 4, 5. When your hand gets to the very bottom here, it gets a little bit tingly, and so it's because you had like some blood here, and your blood vessels couldn't provide, you have this upwards acceleration that you need, and the blood vessels couldn't provide that acceleration. So what happens is that they don't stay on the path, and instead, it kind of moves down relative. Your hand, stays in the path because your shoulder is strong enough, but the blood isn't. So it kind of keeps like going on a downward path like this, right? And it ends up down here until finally the ends of your fingers, your skin is strong enough to push it back, right? Your skin is much stronger barrier there than your blood vessels, right? And so effectively the blood moves down in your fingers, right? That's not really what happens. Actually, the blood stays in a straight line and your hand moves, but effectively it's the same thing as your blood just kind of pulling up in your fingers. Well, the same thing can happen in your brain. If you can't accelerate the blood in your brain or the blood in your whole body quickly enough upwards, then that blood would leave your brain and you would experience something called a blackout, right? So we have to limit, how quickly she can accelerate upwards, or centripetal acceleration, so that she doesn't black out, right? Because that would be kind of tragic. So this is why we have this kind of maximum centripetal acceleration here of 4Gs. Now we can calculate our minimum radius pretty easily. Probably shouldn't have erased that, but the radius is going to be this, right? We'll have our minimum radius if we maximize the centripetal acceleration, right? Centripetal acceleration is v squared over r, right? So when r is a minimum, the centripetal acceleration is a maximum, right? We have this inverse relationship here. So we can find our minimum by choosing maximum centripetal acceleration. And this maximum centripetal acceleration, that's 4G, so that's 4 times 9.8, right? So, that's 39.2 meters per second squared, just to kind of put a number to it there. Sometimes we refer to it in multiples of G because that's like multiples of your weight, which I can talk about in a minute here. So for part A, it's pretty straightforward here. We'll just say, all right, if we have the centripetal acceleration is equal to v squared over r, then this means that our minimum radius, our minimum, is going to be equal to v squared over the maximum centripetal acceleration, right? We have v, and so then the minimum radius, our minimum, is going to be 95 squared over 39.2, and this comes out to 230 meters. So she's going to go through a vertical circle at this speed. Then she needs to make sure that her turn radius is 230 meters, or she risks blacking out. Okay. Chances are there's a little bit of like a safety factor in here. Maybe she could actually go up to like 45 or something, but we're just being safe. And then part B says, what is the apparent weight of the pilot at the lowest point of the pullout? So what is the apparent weight? So how heavy does she feel? Her actual weight is just mg, but she can feel heavier or feel lighter depending on her acceleration, right? If you're in free fall, you feel weightless, although you have a weight of mg. So for part B, let's draw a free body diagram, right? The apparent weight, that's a force, so we would need to analyze the forces. So I have an x and y component here. Remember, she's going down like this. I'll draw a free body diagram of her at the bottom. And I have a normal force exerted on her, like by the seat or something. There's her weight, right? Her actual weight. And then there's the required acceleration for her to stay in this circular path, right? So we can sum the forces in the y direction equals mass times acceleration in the y direction, which in this case is the centripetal acceleration, right? So we get normal force minus the weight is equal to mass times the centripetal acceleration. And so we have the normal force, which is, that's what her apparent weight is. It's the normal force, right? It's the force that the chair pushes on her. It's how heavy she feels at that moment. This is going to be mg plus mac. But the centripetal acceleration was limited to 4g, right? So 4 times the acceleration due to gravity. So if I plug that in here, then the normal force is equal to mg, that's her weight, the normal part, and the usual part, I should say, not normal, not the same as here. And plus m times 4g, right? So which I can kind of move this around. I'll call this 4mg. So this is, 4 mgs. That's 4 times her weight. And that's kind of why sometimes we give centripetal acceleration or accelerations in general in terms of g, because then if I multiply it by m, I can get it in terms of the weight, right? So I can kind of think, if I'm accelerated at 9.8 meters per second squared, the force on me is going to be the same as my weight. If I'm accelerated at 2 times 9.8, whatever that is, like 19.6 meters per second squared, if I'm accelerated at 19.6 meters per second squared, that means I'm going to have twice my weight pushing on me, right? So, that I can start thinking like, can my knees really handle that if I'm pushed upwards that speed, So kind of things like that, right? If you have like 200 pounds, then like if you're accelerated upwards at 19.6 meters per second squared, that's 400 pounds of force, right? So that's a lot. Anyways, so this is what we get here. Basically, the normal force is 5 mgs, 1 for her weight, 4 for her acceleration upwards. And so this is equal to 5 times her weight. So 5 times, I believe she was 50 kilograms, times 9.8 meters per second squared, 2,450 newtons, right? Which is, 5 times her weight. Normally she's just 50 times 9.8, right? So normally only 500 newtons, quite a bit more. But yeah, so in vertical circles, important thing there, you have to remember that weight is playing a role as well, right? You always have to remember if I have, something going on in a vertical circle, then you gotta be careful that you got a normal force and a weight, upwards acceleration. So if I have this upwards acceleration, um, then I'm going to be heavier, right? Or I'm going to feel a lot heavier. My apparent weight's going to be more because I have my own weight I have to deal with, plus a force to accelerate me upwards.